Okay, welcome back. Today I'm going to be going over waves and principles of waves in physics. So, what can be classified as a wave is anything that has a repeating or periodic disturbance that may move through a medium from one location to another. It's classified as a wave. So, there's a few terms that you're going to need to know here, such as a disturbance and a medium. Um, but in short, for at least for modeling mathematically, anything that has a repeating motion can be classified or modeled as a wave. So think of a clock. It repeats, the minute hand repeats its motion every, let's say, well, yeah, 60 seconds. And then hour hand repeats its motion every 12 hours. Uh, the Earth itself rotates and basically repeats its motion every 24 hours. That kind of thing. That can be modeled mathematically as a wave. All right, a wave transports energy and not matter. This means waves are energy transport phenomenon. So what does that mean? We'll look at this in a second. We're going to look at mechanical waves first, just to kind of see how it just transports the energy through a medium. But the direction of energy transport, so the way the energy is moving, is called the propagation. So this is the direction the energy is moving. The distance that a particle or a body is displaced or moved from its equilibrium or rest position is called disturbance. So this is kind of wordy, but basically this is just how much the medium or the particle moves up and down or back and forth to move the energy. And let me talk about mediums really quick. So what are mediums? So mechanical waves are transported through a medium. Medium is the substance that carries the wave. These two sentences are virtually the same. Uh, Mediums are just the thing that the wave moves through. So, like waves on a surface of water, if you look closely, the water itself ultimately has not moved. It'll move up and down, but the location of the particles really doesn't change that much. What does change is the location of the kinetic energy of whatever splashed in the middle and then what's radiating outward. Now, if you look at a wave in a stadium, which is kind of a weird example, but if you look, the people might move up and down. That would be the disturbance. And the people themselves would be the medium, that they're the thing that the energy is moving through. But ultimately, the people start sitting down and they end sitting down. They haven't moved. Okay. So let's look at different types of waves. We've got transverse waves. So transverse waves move perpendicular to the propagation. So if the energy is going this way, then the disturbance is going up and down. So again, if the perpendicular energy is moving sideways, disturbance is going up and down. This is usually what we think of visually when we think of a wave. It's a transverse wave. All right. The next type is a longitudinal wave. So longitudinal waves are characterized by the motion being parallel motion. So if you've got propagation moving sideways, the disturbance is also going to be moving sideways. And basically, what it looks like is it's represented here with a slinky. When you're actually talking about a sound wave, because it says down here sound waves are a classic example of a longitudinal wave. If you're talking about a sound wave, it's actually the air particles bumping into each other and carrying that message or that energy, the sound information uh, through the air or through whatever medium it's traveling through. All right, an electromagnetic wave is a wave that's capable of transmitting energy through a vacuum. Okay, so these types of waves do not need a medium. Uh, these can propagate themselves without going through medium. Now, they can go through mediums, but they do not necessarily need one. And some mediums will actually stop them, just as some mediums will stop mechanical waves. A mechanical wave is not capable of transferring energy through a vacuum. It needs a medium. So something like sound, you could hear, you've probably heard before that there's no sound in space. That's just because there's no air or no water or anything to actually transport the sound from the source to your ears. Okay, the anatomy of a wave. So we're looking at a transverse wave here. So the dashed line in the middle represents the equilibrium or the rest position. So this is where the particles would be, or the medium would be, if there was no energy moving through it. So the crest of the wave is the very top, is the most positive or upward displacement of the particles from rest position. But you can just think of it as the top of the wave. So the trough is the exact opposite. That's like points 3 and 4. So that's the most negative downward displacement. So that's how much it has been displaced downward. The amplitude of the wave is the distance from the equilibrium. So if you cut right through the middle of the wave, that's the equilibrium. The distance from either the equilibrium to the crest or the equilibrium to the trough should be the same amount in all the waves we're working with. And then the wavelength is the length of the wave to complete one cycle. So you can go from crest to measure, or you could go from trough to trough. All the waves we're going to be working with will be they will be the same. All right, longitudinal waves. You have a compression. So I have compressions here. That's where the particles are, or the medium is bumping into itself to move the message along. So if it's propagating from like left to right, this is where the energy is, and it's getting bumped into the rest of the medium. And the rarefaction is where the matter is most spread out. So it's in between the compressions. And then, of course, wavelength is still the length between two complete cycles. So you could go from compression to compression or rarefaction to rarefaction. Okay, last couple things. So the frequency of a wave, or the frequency of anything, refers to how often that thing happens. So how often does it happen is the frequency. Frequency is measured in hertz. So a hertz is how many times something happens every second. So 1 hertz would just mean it happens 1 time a second. 12 hertz means it happens 12 times per second. A period. A period refers to the time it takes for something to happen. So if I wanted to say the period for a day, a period for a day is 12 hours. I'm sorry, 24 hours. And then if I wanted to say the period for a year, the period for a year is 365 days. Kind of get the idea. So with waves, a period is the time it takes for a wave to make one complete cycle. So crest to crest or trough to trough. But the time, not necessarily the length. All right, so, and if I look at these things, a period and a frequency are inversely proportional. So that means if one goes higher, gets bigger, the other one gets lower. So a period, and that makes sense. Like your period would be very short if things happen a lot. And our period would be very, very long, like a year, if things don't happen that often. If it takes 365 days is my period for a year to happen, my frequency would be very, very low. It doesn't happen except for once a year. So a period is equal to 1 divided by the frequency, and the frequency is equal to 1 divided by the period. And finally, here are your formulas you can use to find the speed of a wave. So the speed of the wave is equal to the wavelength times the frequency. So If you have period and you don't feel like converting to frequency, which is just 1 divided by frequency equals period, my speed is also the wavelength divided by the period.